Hello. In this session, we will understand what is power and Poynting vector. Generally, in wireless communications, how electromagnetic energy is transmitted. If you take a, that means how energy is transmitted from one point to another point. So whatever we transmit, that is energy, it is transmitted from transmitter to receiver by electromagnetic waves only. So to understand this electromagnetic wave energy being dissipated at a free space, we must know what is the Poynting vector. Okay, now we'll see that. This Poynting vector will derive from Maxwell's equations. Now I'm taking here two Maxwell's equations. Equation 1. So del cross E is equal to minus mu dou H divided by dou T. Equation 2, del cross H is equal to sigma E plus epsilon dou E divided by dou T. Now I'm taking equation 2. So on both sides of equation 2, I'm making dot operation of E. So equation 2, I'm applying dot operation with the E. So E dot is here, E dot del cross H is equal to, so sigma E dot E is E square plus E dot epsilon dou E divided by dou T. So that is, actually it is a dou T. So that is equation 3. Now see that in this equation 3, we have two vector fields, that is electric field and magnetic field. If it is so, we can apply one vector identity. The vector identity is, if there is two vector fields involved, then we can have a del dot A cross B is equal to B dot del cross A minus A dot del cross B. So I am going to apply this vector identity to this equation 3. How is, in the place of A, I'm going to write H. In the place of B, I'm going to write E. That means magnetic field and electric field are replaced in the place of A and B respectively. So now we can rewrite equation 3. H dot, so H dot del cross E plus del dot H cross E is equal to sigma square plus E dot epsilon dou E divided by dou T. So after applying vector identity, I just rearrange the equation 3. From that, I got these equations. And see here, sigma square plus E dot epsilon dou E divided by dou T is there. So this can be expanded now. Now we will write. So for example, I'm taking here dou E square. I'm taking here dou square by dou T. Or we can write it is dou E dot E divided by dou T. Let me write dou E square divided by dou T is equal to dou E dot E. That means E square I'm writing like this. So now I'm applying here, the formula is UV formula. So differentiation in UV formula. So first time I'm differentiating this E with respect to this. The same way, this E with respect to this E. So that you are applying here simply UV formula. So the result will be dou E divided by dou T plus, so U dV by dt. Now B du dt divided by dou T. So both are same only, so that it is equal to 2 E dou E divided by dou T. See that here we have the term E. Here we have term E dou E. This means this can be like epsilon E dot dou E divided by dou T. We can write this. So see here. So E dot dou E divided by dou T. Here it is available. So that E dot dou E divided by dou T is equal to dou E square by dou T square by 2. So that in this place, we can write 1 by 2 dou E square divided by dou T. Sorry, not here T. Okay. So 1 by 2 dou E square by dou T only. So that here sigma equation 4 after applying vector identity and rearrangement, we got sigma E square plus E dot epsilon dou E divided by dou T. This component is written as 1 by 2 epsilon dou E square divided by dou T. That is equation 5. Now again I'm applying the dot operation to the equation 1. See that equation 1 is here. So now in this case, so equation 2, I applied a dot operation with the E. And in this equation 1, I'm applying dot operation with the H. See here. So here H dot I'm making here. So here also I'm making here H dot. So equation wide I handled. So after applying dot operations, equation 1 becomes H dot del cross E is equal to H dot minus mu dou H divided by dou T. And previously we found the relations. If E dot dou E divided by dou T means, which is equal to 1 by 2 dou E square by dou T. The same way, if it is H dot mu dou H divided by dou T, you can write it is as 1 by 2 dou H square divided by dou T. So that in equation 6, okay. So equation 1 is applied a dot operation with E. Now we get it is H dot del cross E is equal to these two terms. And check the equation 5. In equation 5, we have H dot del cross E. So here we have a H dot del cross E. So that in equation 5, I'm applying this. Okay. So in equation 5, I'm applying this. So I'm going to substitute this into equation 5. So if you substitute these things into equation 5, so here we get, see here, equation 5, sigma square plus 1 by 2 epsilon dou E square by dou T. The same here in this from equation 6 substituted. So minus mu 2 dou H square, because this can be written as minus mu by 2 dou H square by dou T. Okay. So in this term, we are writing this. So minus mu by 2 dou H square by dou T minus, see here, plus del dot H cross E. So I'm reversing this. H cross E. I'm making it as rearranging this. So E cross H, so that it becomes minus. So minus del dot E cross H, which is equal to sigma square plus 1 by 2 epsilon dou E square by dt. So sigma E square plus 1 by 2 epsilon dou E square by dt. So this is equation 7. Again, we rearrange these equations. That means del dot E cross H is in this side and is equal to, so this comes here. So after rearranging this, so I'm applying here divergence theorems. So if you apply divergence theorems, so it becomes, so del dot E cross H here, the number 2 terms, 1, 2, 3, three terms coming this way. Okay, so after applying divergence, So del dot E cross H is equal to, so 1 by 2 sigma E square, 1 by 2, so mu H square under sigma E square. This is the result. So if we apply divergence theorems, so the result will be, so volume integral becomes the closed surface integrals. See here, so here del dot E cross H, which is after applying divergence theorem becomes, so closed surface integrations. So E cross H dot ds is equal to, so volume integration over, so dou by dou t 1 by 2 epsilon E square plus 1 by 2 mu H square minus sigma E square. So from these equations, what we understand is the total power leaving the volume, that is through surface of the volume, is equal to rate of decrease in energy stored in electric and magnetic fields minus ohmic power dissipated. This is the Poynting vector. That means from the Poynting vector, we understand that the net power flowing out of a given volume V is equal to the time rate of decrease in the energy stored within the volume. That energy is electric and magnetic fields minus the ohmic power losses. So this is the Poynting vector concept. Thank you.